So, before we let Leo jump into this experiment, let me explain Newton's three laws. The first is the law of inertia. An object at rest will remain at rest unless acted upon by an unbalanced force. An object in motion continues in motion with the same speed and in the same direction unless acted on by an unbalanced force. This means that an object will have a proclivity to keep doing whatever it's doing, that being either motion or rest. The second law is force is equal to mass times acceleration. This means that it will take more force to move something of greater mass, and when something has greater mass, there will be more force. This is the same with acceleration. More acceleration equals more force, and more force will have to be applied to move something in the opposite direction of its acceleration. The third law is every action has an equal and opposite reaction, meaning that when a rocket takes off, it's not the rocket that makes itself fly, it's the ground pushing back with an equal and opposite force of all the energy being exerted on the ground. That's what makes it fly. Now you're probably wondering why I chose to have space in the video. The reason for this is quite simple. These three laws govern all motion in the entire universe, and space is a pretty good representation of the universe as we know it. Anyway, I'm done with my talking. Let's jump into Leo's experiment, shall we?
Now, in Newton's third law of action-reaction forces, that shows that if I push on something and I don't move it, it's going to push back on me. That means it's because it did push back on me. Example 1. The wall was unable to be moved, so it moved me because of the force.
This was also an example of Newton's second law. This is because Leo was unable to break the wall's inertia, so the wall stayed at rest rather than moving and ultimately crumbling down. Now time to jump into the second example of the second law. I think you guys will enjoy this one.
So Newton's second law of F net equals ma shows that with different acceleration or mass, the force will be different. In this scenario, the mass is going to be the same. The only thing that will change is acceleration. Let's see if the force changes. Acceleration 1. It just slightly fell off. But acceleration 2.
Now a quick recap of what happened there. In the first example, Leo put a small amount of force into the ball, lowering its acceleration and therefore making the ball and water bottle go less far. In the second example, he put more force into the ball, meaning that the ball's acceleration was higher and obviously the ball went further. Now it's time for us to jump into our second example of Newton's first law.
So Newton's first law of inertia says that this table right here will not move unless there's an unbalanced force that breaks its inertia. So let's see if my pinky does the job. Didn't move. Guess that means it didn't break its inertia. Now, let's see if my both hands can break its inertia. Pretty sure it can though. Yep, I guess it.
Time for a quick recap. The reason he was not able to move the table the first time was because he could not create enough force with his pinky finger alone to move it. But when he pushed with both hands, he could easily do it. This is because the table did not want to move, but once it did not want to stop until he stopped pushing. This is because objects in motion want to stay in motion, and objects at rest want to stay at rest. Now it's time for us to jump into our second example of the third law. Enjoy. So what happened here was I rolled the ball into the wall, and the wall pushed back on the ball with an equal force. This is because Newton's third law states that every action has an equal and opposite reaction. And that's exactly what took place here, a display of equal and opposite forces. Now it's time for us to jump into our final example, the second display of the second law. So what we did here was drop two objects of different masses from the same height. The pink pen cap and the water bottle lid. The water bottle lid had less mass than the pink pen cap, so when we dropped them onto the gram scale, the pink pen cap created less force than the water bottle lid because the acceleration was the same, 9.8 meters a second squared. But the mass was more in the pink pen cap, so therefore the force would have to be larger with the one with more mass due to the second law that Newton created. Force equals mass times acceleration. The reason for the lack of video is due to the fact that the camera was not picking up the max weight when being recorded. but when we took pictures, we could get a clear image of the max weight. That seemed good enough reason to me. Now that we've presented our experiments, my group and I would like to thank you for your time, and if there are any questions or comments, please feel free to ask or say them now.